Right, a double slit interference pattern, two slits here and a double slit pattern there with bright and dark bands. We've got a wavelength of our laser, 612. Here's the interference pattern. This is the central band here, a bright band, which is normal. Alright, calculate, the light energy output of the laser is 5 by 10 to the minus 3 joules per second. That's how many joules of energy it gives every second. Calculate the number of photons leaving the laser every second. What I'm going to do is I'm going to work out the energy of each photon, and then I'm going to work out the number of photons. So the energy of each photon is equal to hc on lambda, which is equal to 6.63 by 10 to the minus 34. Again, I'm always using the same Planck's constant, by 3 to 10 to the 8 over 612 nanometers, 10 to the 9 minus 9, and that gives 3.25 by 10 to the minus 19 joules. Alright, so the total energy is equal to the number of photons times the energy of each photon. So if I want to work out this, the number of photons, to rearrange this equation I get number of photons must equal the total energy divided by the energy of each photon, which the total of energy they've given us there, 5 by 10 to the minus 3, and the energy of each photon is 3.25 by 10 to the minus 19, and that gives me 1.54 by 10 to the 16 photons per second. Explain why the central band, this band here, is a bright band and not a dark band. Alright, so the path difference to centre band, path difference between both those slits is equal to 0. Because the path difference is 0, therefore constructive interference occurs. Which is a bright spot. To see, it's the same diagram, and they say another point on the pattern is further from slit 1 than slit 2 by a distance of that. So when something's further from slit 1 than slit 2, they're saying the path difference equals that. Its position is to the right, so its position is over here somewhere. Indicate where this is by writing the letter X exactly above which one it is. We know each one of these, this is 0 wavelength path difference, we know this is 1 wavelength, we know this is 2 wavelength, this is 3 wavelength, this is 4 wavelength, and the ones in between are obviously half as well. We've got to work out how many wavelengths is this path difference. So path difference equals 2.142 by 10 to the minus 6, and usually it equals n wavelengths. So let's go 2.142 10 to the minus 6 and divide it by lambda to get n, which is 2.142 by 10 to the minus 6 over 612 by 10 to the minus 9. Put you that in your calculator, and you get 3.5 out. So that's 0, 1, 2, 3. 3.5 is this guy here. So we've got to put an X above it. That's what they've asked us to do. And the last question in this set So I've got the same bit at the top, and then this is the new part. Another laser produces light of a different wavelength. The pattern is now spaced more closely. 4A shows new pattern, 4B shows the original pattern. This is the original pattern with lambda equals lambda old, we'll call that old, equals 612, and this is the new one, lambda new, makes this pattern. The second bright band to the left in the new pattern, here, is at the position of lambda y. The original pattern, this was the position, so this is directly on top of a dark band. Because they're in the same spot, the path difference of the new and the path difference of the old is the same at these points y. At y, path difference new equals path difference old. Now this is 0, 1, 2 wavelengths out, so we know 2 of the new wavelengths because path difference equals n lambda. So I'll put n, which is 2, is equal to, how many of this one? Well, there's 0, there's 1, 1.5. 1.5 of lambda old. We want to find lambda new, so we rearrange, divide both sides by 2. Lambda new equals 1.5 over 2. Lambda old is 1.5 over 2 times 612 nanometers, and that equals 459 nanometers.